we'll start our course on electricity. Now, electricity, when we study electricity, we study these things. First is electrostatics. What is electrostatics? It means when the charges are at rest, not in motion. This is electrostatics. Second is, we'll read when charge is in motion. So that is called electrodynamics. Electrodynamics. We'll also study magnetism, though it is part of this. I'm writing it separately. We'll study what is magnetism and specifically electromagnetism. We'll see how charges create magnetic fields and how charges behave in magnetic field. And we'll see interaction of electric and magnetic fields. So these are the topics that we'll see. We'll see each topic in detail, understand the concept, and we'll solve many examples to understand the topic. And then we'll move to, after studying electrostatics, electrodynamics, all of magnetism and everything, then we'll move to semiconductor physics. So let's start with this. And we won't waste time in describing topics that are not useful. Okay, for example, charge. We all are acquainted with this term charge. When a glass rod or plastic, anything is rubbed against silk, you will find some sparking. These are charges. So let's not waste half an hour on what charge is. We know there is a charge which is generally denoted by the term, by this letter Q, small or capital letter Q. In physics, we generally represent it by this letter. And we know that charges are of two types. They could have been said charge of type A and charge of type B, because charges are of only two types. But an American scientist, Benjamin Franklin, he used the term, or he coined the term negative and positive. So there are two types of charges. One is called negative and another is called positive. You must understand there is nothing negative about this charge or anything positive about this charge. It is just convention that one type of charge is called negative and another type of charge is called positive. Okay. Now, we have seen atom. We have a nucleus in which we have protons and we have neutrons that are uncharged. Neutrons are uncharged particles. And around the nucleus, we have several small charges that orbit the nucleus. These charges are called electrons. Protons have positive charge and electrons have negative charge. The charge on each proton is plus E proton, and charge on each electron is minus E, where E is, the value of E is 1.602 into 10 to the power minus 19 coulombs. Coulombs is the SI unit of charge. Okay, so you know about this, the atom, nucleus, proton and neutron. Proton is positively charged, electron is negatively charged. Clear up to this? These protons and neutrons, they are composed of subatomic particle, that is, or you can say not particle, subatomic entity, that are called quarks. They have this, or they have 1 by 3 and 2 by 3 E charges. So they actually compose a proton or a neutron, giving it plus E charge and making the neutron neutral. So this is all the basic thing we should know about charge. These things you know from your school days only, you have studied these things. So we'll move forward. Now, what are the properties of charges? So basic properties of charges. The first property of basic property of charges, electric charges, is called additivity. What is additivity? Try to understand it properly. Let's say we have a space, a sphere. Okay, this space is a sphere, and inside this sphere we have so many charges: Q1, Q2, Q3, minus Q4, minus Q5, minus Q6, and so on. Okay, this is a space. Let's understand this as an isolated space. That is, it is isolated from other charges if there are any around this. This is an isolated system. Isolated means isolated from its environment. We are not considering charges near this and around this. So this is an isolated system. Additivity means if you want to know what is the total charge inside this sphere, you can say this, you will simply add all the charges with its polarity. That is, here we have Q1, Q2, Q3 as positive. So Q1 plus Q2 plus Q3 and then minus Q4, then minus Q5 and minus Q6. Okay. So the total charge inside this sphere, if we want to know what is the net charge in this sphere, we'll simply add it. So if we say Qi, then total Q will be I equal to, if we have n number of charges, so we'll simply add all the charges with their polarity. If Q7 is plus, we'll say plus Q7. If Q11 is minus, we'll say minus Q11. So this is the first property, which is called additivity. Second property of electric charges is that it remains conserved. That is, at for an isolated system, the total amount of charge remains conserved, or the total charge inside it remains conserved. What is the meaning of this? Let's say these are the charges spread across this sphere, and somehow we introduce a glass rod here. Now let me use another color. This is a glass rod inside this. Okay, so this is a glass rod, and Q1, Q3 minus Q5, these charges stick to this glass rod. So when we talk of this sphere without this glass rod, that is, what are the charges available inside the sphere excluding the glass rod, then we'll say we have Q2 minus Q4 minus Q6. These are the charges available inside the sphere which are not on the rod. But if we say what are the charges, what is the total charge and what are the charges on the rod, we'll say plus Q1 minus Q5 and then plus Q3. So this is inside sphere sans rod, and this is on rod. But if we talk of this whole system, what is the total charge in this, then it will be this plus this. That is your same as Q1 plus Q2 plus Q3 minus Q4 minus Q5 minus Q6. That is the charge, the total number of charges remain conserved. In a system, it only flows from one system to another, but if you talk of an isolated system, it remains conserved. Clear? That is, if a glass rod is charged, is rubbed against a silk, silk, we may have hundreds of positive charges flowing from the rod to the silk, or thousands of charges, negative or positive, flowing from the silk to the rod. But the net number of charges, if we had taken in the start the number of charges in the on the silk surface, on the surface of the silk and on the surface of the rod, it will remain same. Only it gets transferred from this place to that place. But in an isolated system, the number remains conserved. Okay. The third property is quantization of charge. Quantization of charge. What is quantization of charge? Any charge, any particle or point charge, if we represent it as Q, it is always equal to an integral multiple of E. Integral multiple of E, where E is, 1.602 into 10 to the power minus 19 coulombs. So whenever you have, let's say this is your point charge Q. What is the meaning of point charge? Point charge means it has no spatial dimensions. That is, this has no length. You cannot consider it as a sphere with some radius. It is point. It has no spatial dimension. So if you consider Q, it has to be some multiple of E. Let's say 10 of E, 12 of E, 10,000 of E, 1 lakh of E. But it will always be a multiple of E. So these are basically called the basic properties of charge. We'll consider them when we'll solve problems. We'll try to understand its meaning in a more practical way. Now, the next important thing or next important concept in electrostatics is called Coulomb's law. Coulomb's law. What is Coulomb's law? Let's say we have two charges. We have two charges Q1 and Q2. This is Q1, this is Q2. Okay. Now, Coulomb's law states that the force, the magnitude of force between the two charges or on one charge because of another is proportional to the magnitude of product of the magnitude of these two charges, that is Q1 into Q2. The magnitude, not on the direction. I'm talking of magnitude of it. So it is proportional to, directly proportional to the product of the two charges, the magnitude of the two charges, and is inversely proportional to the distance between them. If this distance is r, we say it is inversely proportional to this. This is Coulomb's law. This is half of Coulomb's law. Force is a vector quantity. So this actually gives you the magnitude. What about the direction? Let's say this line joins these two charges. Then the next part of Coulomb's law states that it is directly proportional to the product of the two charges, inversely proportional to the square of the distance between the two charges, and acts along the line joining these two charges. That is, force acts along this line. Clear? I'll explain this again. First of all, let's write this. Let's see what is the magnitude. I'm just writing F, not vector F. That is the magnitude. So this is to get rid of this proportionality. What we do? We put a constant. So this is K Q1 Q2 mod of this, because it may, these two may be different charges. So this is this thing, K into Q1 Q2 by R square, where K is this constant has been experimentally found to be 1 by 4 pi epsilon naught. What is epsilon naught? Epsilon naught is the permittivity. It is a property, permittivity of vacuum. So it is a property of the medium. It comes to, it has a certain value. Let me give this value, K equal to 1 by 4 pi epsilon 0. This is almost equal to, it is 8.987. So almost equal to 9 into 10 to the power 9. What will be the unit? Say unit. This into this. So this is Newton, this is meter square. So Newton meter square by Q1 Q2, Coulomb square. Okay. So this is the value of K. We will be frequently using this. And value of this is 8.854 into 10 to the power minus 12. This is inverse. So the unit will be just reverse. Coulomb square, Newton meter square. Okay. So this is about the magnitude. Now let me explain you the direction of this force. Okay. This is clear. What will be the direction of the force? Now force is a vector quantity. You know it. So if we talk of force on charge Q1 due to Q2, or we can talk of force on charge Q2 due to Q1. Okay. Then let's say this is origin. So we'll talk of, this is origin. So we'll talk of position vector. You must have studied vector. If you are not very familiar with vector, you should go and refresh your vectors first. So let's say the position vector here is R2 and position vector here is R1. So here to here we'll write 2, 1, which will be R2 minus R1, which will be in this direction. So R2, 1 is this. So if we talk of force on Q2 due to Q1, so we may write it as F21, force on 2 due to 1. And when we talk of this, we'll say force on 1 due to 2. Let's see what is the value. See, force on 2 due to 1. This will be given as, you know, this is 1 by 4 pi epsilon 0 Q1 Q2 mod by R. Let's say both this R1 and R2 both are R. So this is R square, and the direction here will be this one. Okay, R21, that is this to this. So we'll talk of R21 unit vector. What is unit vector? You know, R21 will be, this is equal to R21 by mod of R21. This is unit vector. So force on 2 due to 1 will be in this direction. Okay. And force on 1 due to 2, this will be R12. Okay, and you can see R21 and R12, they are 180 degrees apart. So you can say R21 is equal to minus R12. So from here you get F12 will be equal to minus F21, and this actually satisfies Newton's third law, that the forces act in different directions, in opposite directions. They are equal in magnitude and opposite in direction. So this is Coulomb's law. And what we get from Coulomb's law? We get the value of force due to charge or a number of charges, or to say like this, we get the value of force due to a charge on another charge. Okay, and these are the magnitudes and directions. Now let's understand force on a charge due to multiple charges. From here only we can understand the force experienced by a charge due to multiple charges. Let's say this is Q1, this is Q2, and this is Q3. I'm taking 3 charges, and we have a charge Q here. So force on, let's say this is Q naught. Force on Q naught due to Q1, this will be, let's say 0, 1. Force on Q naught due to this will be F2, not F2, F0, 2, and force due to this will be F0, 3. Now these 3 are vectors. So if you have multiple charges, the net force on that particular charge will be the algebraic sum of all these forces, but that is algebraic vector sum of this. So this will be F01 plus F02 plus F03 and so on. If you have so many charges, these all will be vector. You have to do vector addition. How vector addition is done? You must have studied in vectors. If you are confused, you can take one direction, then angle between them, and you can resolve cos theta and sin theta, and then you can take it. Okay. So this is how we take force on a particular charge because of many charges. And one thing I should have said in the start only, you know that opposite charges attract. Opposite charges attract. That is, plus Q and minus Q will attract each other. The force will be inwards on the line joining the two charges. But same charges repel. That is, if you have plus Q and plus Q on this line, they'll repel. The forces will repel each other. Or minus Q and minus Q, they will repel. This is unlike gravitational force. In gravitation, we have only masses. We don't have two types of masses, plus mass and minus mass. So gravitational forces always attract. But electrostatic, when we are talking of electric charges, there are two types of charges, and opposite charges attract, same charges repel. Let's understand something. You can take it as example. This is the mass of proton, mass of electron, and charge on one electron is this. I have given the values. If we have an electron and a proton, okay, this is an electron, this is a proton. We want to know what is the force of, obviously, attraction, that is electrostatic force due to these charges, between these charges. So electrostatic force, if I say this Fe, obviously it will be attractive. So what is the value? It will be 1 by 4 pi epsilon 0, and then Q1, Q2, that is E square, and then distance, let this distance be D. So this will be D square. And what is the force of gravitation between these two? This will be G, mass of proton into mass of electron, by distance square. Now let's find out the values of this, and let's see the ratio between two, so that we have a fair understanding of the strengths of electrostatic force and gravitational force, just for understanding. So this will be 9 into 10 to the power 9, this K, e square. So this will be 1.602 square into 10 to the power, see, it is e square, so this is 10 to the power minus 38. Distance, let's say our distance is 1 angstrom. What is angstrom? You know, it is 10 to the power minus 10 meters. So d square, so this will be 10 to the power minus 20. What is the value? Let's see. 9 into 1.602 square. So it comes to, I'm writing it here, 23.09 into, see, this will go in the numerator and this will become positive. So this will be actually 9 plus 20 minus 38. What is this? 9 plus 20 is 29, and then this one. So this is 10 to the power minus 9. So what we get is this, the value will be 23.09 into 10 to the power minus 9. This is 4, so this is Newton. Okay. Now let's see what is the value of this one. The value of G is 6.67 into 10 to the power minus 11. And if you talk of unit, it will be Newton meter square per kilogram square. Okay. So this is 6.67 into 10 to the power minus 11. Then we have mass of proton 1.67 into 10 to the power minus 27. Mass of electron is 9.11 into 10 to the power minus 31 by distance square again 10 to the power minus 20. Okay, let's find the value. It comes to 101.47 into 10 to the power minus 49. Okay, so this is the value. You can say, see, this is 10 to the power minus 9 and this is this. What about the value? Now, if you try to find the ratio, then the picture will be more clear. If we take Fe by Fg, obviously we are talking of the ratio of magnitude only. It will be 23.09 into 10 to the power minus 9 by 101.47 into 10 to the power minus 49. So what you can do, you can put this minus 10, so that this is 230. So what is 230.9 divided by 101.47? It comes to 2.28 into, this goes to this side, this is 39, 49 minus 10, 30. So you can see the electric force, the Coulomb's law, Coulomb's force between the two charges is 10 to the power 39 times the gravitational force between the two charges. So this is such a weak force in comparison to this electric force, electrostatic force. Okay, so this example I gave you to have an understanding of 2-3 things. First, how to calculate Coulomb's force, then how to compare Coulomb's force with gravitational force. So you should have an understanding of the, we say this force is a weak force, this force is a strong force. So what is the difference? You can see this is 10 to the power 39 times that of the gravitational force acting on this. Okay, so if we are talking of this Q1 and then below it we have Q2. If I ask you what is the force experienced by 1 due to 2, there will be gravitational force also, but that will be so low, that will be so inferior to the electrostatic force that it is almost, or not it is almost, it is negligible in comparison to the electrostatic force. So you will have to compare, you will have to consider only the electrostatic force. You will just ignore the gravitational force of attraction between the two charges. Okay. So you saw the question. The question says we have 3 charges. Let this be Q charge. And we have 3 charges. Let this be Q1. Let this be Q2. Where to put Q2? Let it be here. Q2, and let there be Q3 somewhere, Q3. Okay. The question says the position vector of Q is R. Position vector of Q1 is R1. Position vector of Q2 is R2. We have to find the force due to Q3 in terms of these variables Q1, Q2, Q, R1, R2. So position vector, what is the meaning of position vector? If this is your XY plane, this means this is your R1, this is your R2, this is R. This is the meaning. For this it will be R3. We have to find force due to this Q3 on this Q charge when this charge is in equilibrium. That is, the force exerted by Q1 and Q2 on Q will be equal to Q3. Then only it will be in equilibrium. So what is this force? Let's see. This is first charge due to 1. So let it be F1. What about this? All are positive charges. So let this be F2. So this is F1, this is F2. Now, you know, if this charge is to be at equilibrium, that is at rest, the force due to Q3 must balance the force due to the net force due to this. So what will be the net force due to this? You know how to, this will be the net force. Let this be F by parallelogram method. This you know. So let's see what is F1, what is F2. What will be this distance? This is R1, this is R. Okay. So what will be this distance? This plus this will be equal to this. So this will be this particular, this plus this. So this will be R minus R1. Okay. Again, this plus this will be this. So what will this be? This vector. This will be R minus R2. Okay. Now we calculate the force, the first force, that is force on point charge Q due to Q1. What it will be? F1. This will be 1 by 4 pi epsilon 0 Q into Q1 by R square into cap of R cap in that direction. So what will be R? R is R minus R1. This is your distance. So what do? We take square of this and we take cap of this. That is unit vector along the direction, along this direction. This is Coulomb's law. What is unit vector? You know, this can be represented as, if you take unit vector of this, you can write it like this: R minus R1, the vector, by modulus of this vector. So if you put it here, this will be cube. So let this be the vector and this will be cube. Okay. So this is F1. What is F2? That is force on charge Q due to this Q2. This is your Q1, this is your Q2. So F2 will be 1 by 4 pi epsilon 0 Q into Q2 by R minus R2 cube, and then this vector. Okay. And you, as I told you in the start only, that force due to 3, if this charge is to be at equilibrium, then force due to 1, force due to 2, and force due to third charge on this particular charge Q has to be equal to 0. We have to find F3. What is F3? It is minus F1 plus F2. We have F1 and F2, so we can write minus 1 by 4 pi epsilon 0. You can also take Q out, Q by 4 pi epsilon 0, and then Q1 by Q1 are this vector by cube plus Q2 r minus r2 by r minus r2 q. So this was the requirement to express third force in terms of q, q1, r, r1, r2 only. So we have expressed it. So I guess this is clear to you how we use vector to analyze the electric force between charges, multiple charges. And one thing must be remembered, that this is basically the magnitude only. So you can write like this also. In place of bracket, you can simply put modulus, because we won't be taking direction. So it is better to put it like this. The upper one, numerator one, is vector, while the denominator is only magnitude. Okay, clear? Now you must have understood the question. The question says we have this equilateral triangle and three charges are placed at the vertices of this equilateral triangle. Let this be Q, Q and Q, all are Q. The question says the side of the equilateral triangle is L. Now, as per the question, at the centroid, you know what is centroid? It is 90 degrees to the next side. The question says at the centroid of this triangle, equilateral triangle, we have placed another charge Q. This means the charge is at equilibrium. When it is placed at this point, it means it is at equilibrium. What is the net force on this charge? Obviously, the net force has to be 0, then only it will be in equilibrium. So how to find it? Let's see. There are several methods to analyze it. The best method is, see this figure. I am putting it here. Okay, so this is this point. Q is placed here. Now, one force will be from this Q, this is small q, this force F, then this force F, and then this force F. Why I am using F? Because all the charges are same. So Q by R square. So we have F in this direction, we have F in this direction, and we have F in this direction. What we'll do, we'll resolve it. How to resolve? Let's say this is our x-axis, this is our x-axis, and this is our y-axis. Okay, y-x. You know, this is a 90 degree, this is 30 degree. So this angle will be 60. So this angle will be 30. So this angle is 30 degree. Clear? This is also 30 degree. What about this? We'll be having components of force in x and y direction. If this is the force, F cos 30 will be in this direction and F cos 30 will be in this direction. Therefore, and this has no component in this x-axis because this is 90. So what happens? F cos 30, this is equal to, or you can say if you analyze in any direction, so F cos 30 minus F cos 30, this is the net force in x direction. To be in equilibrium, this has to be 0, and this actually satisfies. This minus this becomes 0. Clear? So we don't have any pull towards left or right because the forces in both directions are equal. What about this? See, we know that if this force is, the force in the upward direction is, I'm talking only of magnitude, so I'm not using vector notations. F in the upward direction is F sine 30 and plus F sine 30. See, this is F 30, so F sine 30, F sine 30. And in the downward direction it is F. So if these two forces are equal, then there won't be any pull in y-axis, y direction. Let's see, F sine 30, what is sine 30? It is half. So half of F plus half of F, this is equal to F. Therefore, we have F in this direction, F in this direction. So in upward and downward direction, or on the y-axis, the net force is 0. On the x-axis, F cos 30, F cos 30. Net force is 0. Therefore, The total force experienced by this, the net force experienced by this charge is 0. Therefore, it is in equilibrium. Clear? Now, the question says two balls, point balls, are hanging from this a ceiling, and this is like this. Okay, let's say this is M1, this is M2, or it's given M and M. So we have M here and we have M here. The question says angle that it subtends with this is theta. This is theta, this is theta, and this is L. These two balls have charge Q over them and they are in equilibrium. So the question is, what is the angle theta? They derive or deduce an expression for theta in terms of these. How we can do that? By free body diagram. See, this will experience two types of forces. First will be due to gravity. This is due to gravity downwards, which will be equal to mg. You know this. Let the tension in the string will be tensed. Let this tension be T. Here also same. And this is theta, so this will be theta. Okay. And what about this side? Here we'll have electrostatic force. Both charges are of same polarity, so this will repel. So this is Fe, this is T, this is mg. Clear? Now, if we equate, if this is at equilibrium, this means force in this direction will be equal to this direction, to this force, and force in this direction will be equal to this. What is this? If the tension is T, this will be T cos theta. I am writing black, T cos theta, and this side will be T sin theta. To be in equilibrium, we understand that T sin theta will be equal to the electrostatic force, and T cos theta, this one, will be equal to weight. This will balance the weight, then this will be in equilibrium. So this by this, if we divide this by this, it will be tan theta. This is Fe by mg. Okay. So we have expression for Fe from here, which is Fe is, and we are talking of magnitude only. Okay. So we got this. Now, what is this electrostatic force? This is, electrostatic force is 1 by 4 pi epsilon 0 q into q, that is q square, by distance square. The distance between them. What is the distance between them? Now, let's see. Just rubbing it. Let the q be at this point. Okay. This is q. So the distance between this is L and this is theta. So this is L sin theta, this part, L sin theta here to here, and similarly this is L sin theta. So from here to here also L sin theta. Therefore your D is what? D is 2L sin theta. So we can D square, we can do here like this. It will be 4L square sin square theta. Okay. And we have seen this is equal to Fe mg tan theta. Okay. So just take sin square theta to this side. This will be sin square theta tan theta is equal to 1 by 4 pi epsilon 0. Okay. Q square, not Fe, mg tan theta, Q square by 4L square mg. So this is, from here we can apply trigonometry and find theta. The question is to find charge in this form. What will be Q in these variables? We have to express Q in this variable. So Q will be nothing but Q will be under root this into this. So you see 4, this can come out, L can come out. So what you will do, we'll do 4L out, so that we'll get pi epsilon 0. See this is already out, this is out. So mg and then sin square theta tan theta. So we have charge in terms of theta, mg, pi epsilon are constants. So you understood the concept here was to how to solve such questions. If you are given q, the value of q, value of theta, value of whatever, and you can find other values. So what we do, we simply take free body diagram in y direction and x direction, and we equate the forces. Downwards will have weight, that is mg. This side will have electrostatic force. So the tension in the string will be resolved into y component and x component. Here x component is equal to the electrostatic force and y component is equal to the weight. So this way you will be able to analyze and solve questions. Now this question is a step forward to the last question. In the last question, the masses were equal, the length of the string was equal. Here what we have, let's say this is L1 and this mass is M1. This is L2 and this is M2. Different, and the only thing common is that these two lie at the same level because of the electrostatic force. Electrostatic force will be in this direction, and since the lengths are different, therefore this theta 1 and this will be theta 2. This is not theta theta, this won't be equal. It might be of 10 meters and this might be of 1 meter. So theta 1 theta 2. How to analyze this circuit? Not this circuit, how to analyze this situation? Now the only thing given is that theta 1 plus theta 2 is equal to 45 degrees. From here you know tan 45 is 1, so we will be using tan theta 1 plus theta 2. So what to do? Again, let's say this is your M1G. If Fe is to this side, Fe will be to this side also, so this will be common. The charge is Q1, let's say, and here we have Q2. So what will be the force in this direction? Fe will be, see, you can solve any question, I am giving you the concept. Fe will be 1 by 4 pi epsilon 0 Q1 Q2 square, sorry, not Q1 Q2 into the distance square. About distance, you know, this is theta 1, so this will be L1 sine theta 1, L1 sine theta 1 plus L2 sine theta 2 square. So you know what is force, electrostatic force, and the tension in this T1, this will be T1 sine theta, this side T1 sine theta will be equal to Fe, and T1 cos theta, theta 1 only, theta 1 will be M1G. So from here you can get tan theta 1, which is equal to Fe by M1G. Clear? You have Fe, expression for Fe. From here you get tan theta 1 is equal to Fe by M1G. Similarly, similar to this calculation, you can find tan theta 2, that will be equal to Fe by M2G. And you know that tan theta 1 plus theta 2, which is tan 45, that is 1. This is equal to, you must know the expression, tan theta 1 plus tan theta 2 by 1 minus tan theta 1 into tan theta 2. So this is 1. So tan theta 1 is, I am writing it here, tan theta 1 is Fe, see, Fe by M1G plus Fe by M2G. This part is equal to 1 minus Fe square by M1 M2G square. So you have expression Fe and G, you can find the value of Fe. If the value of M1 M2 is given, you can find Fe. You can put it here, you can get other values. So if 2 or 3 or 4 values are given and you have to find another, using these expressions you can solve the questions. You can put numerical values and get the result. Clear? This is the concept.